Hello and welcome everyone to Know Your Scientist series presented by Ahmedabad Academy of Sciences. Today we have with us Professor Raghavan Rangarajan. We welcome you, sir.
Like to know about your early life in childhood. There are certain events or mentors that inspired you to pursue science.
So I grew up in Ahmedabad. My father was a professor in Ahmedabad, and when I was in school, I enjoyed many different subjects, not just science and maths, but also subjects like history. When I was in 10th standard, I was studying for an exam called the National Talent Search Exam, NTSC. And my class, I finished class 10. It was the summer after class 10. And my principal, Father Eric, at St. Xavier's High School, Ahmedabad, asked me to read a few chapters from a book in it to prepare for this exam. And I read the last few chapters, which were on quantum mechanics. And I was hooked on physics and quantum mechanics. Up to that point, in class 10, if someone had asked me, what's your interest? I'd have probably said, I'm interested in these subjects. What do you want to be? Since I hadn't thought too much about it, and in those days, and I think it continues even today, students make some default choices of engineering or medicine or CA or MBA. I would perhaps have said engineer. Okay. But after I read about quantum mechanics in that book, I was about 15 years old. I knew that I wanted to be a physicist. And my journey since then has been sort of following along that track.
Okay, so were there any mentors or any turning point at that time?
So, I think Father Eric influenced me greatly by providing me with this book, though I never discussed physics with him. There were one or two teachers when I was in class 12 whose explanations of physical phenomena were extremely interesting, they answered questions that often were glossed over in textbooks. And I found that it just fascinated. Somewhere in 11th and 12th, when I was studying for IIT JEE entrance exam, I picked up Resnick and Halliday. And that book I found was extremely interesting. Once again, it didn't just present physics as here's an equation, this is how you solve a problem. But in the footnotes and in the text of the book, there would often be explanations that were kind of about subtle aspects of the physics phenomena or physical phenomena they were explaining. And I still really enjoyed that. And so in a sense, it's a combination of some books and some teachers who have influenced me greatly.
So your inclination towards theoretical physics was since back then, or there was a certain change after like you did this AP in physics at Princeton University and that PhD at the University of California, Santa Barbara.
Yeah.
So tell me something about it.
So when I entered college, I knew I wanted to get a degree in physics. I think at the end of class 12, you may say I like this kind of physics or that kind of physics, but honestly, it's too early because you have not been exposed to different kinds or different areas within physics. I was fortunate that in my first year in college, actually in my first semester in college, I had a professor, David Wilkinson, at Princeton University, who I used to ask a lot of questions in class. So he one day called me to his office and said, do you want to work in my lab? And so from the very first year in college, I was working in his lab. And then I worked in the lab of someone else in the summer, Professor Dubin, who was then at the Lawrence Berkeley lab at Berkeley. I realized working in the lab that I was not meant to be an experimentalist. I didn't enjoy it, and I didn't really have a knack for it. On the other hand, I really enjoyed mathematics, and as I said, when I was reading textbooks in physics, I enjoyed reading about various aspects of a physical phenomena, looked at from different angles, And so, sort of halfway through my undergraduate years, I realized that my interest was more in theoretical physics than in experimental.
Just so from that part of your life to serving for around, let's say, 2 decades at the app, how did this journey happen?
So I finished my undergraduate degree at Princeton. I wanted to do a PhD. In the US, after a 4-year bachelor's, you join a PhD program, which is really an integrated master's PhD program. That's the standard in the US. There are very few standalone master's programs of physics. They're generally master's PhD combined, and they're just called PhD programs. So I applied to several universities. I got into several universities, but not all. Not all that I would have perhaps liked to go to. But University of California at Santa Barbara was very good, is very good in physics, and in the areas that I was interested in. And so I decided to go there. I finished my degree there. I then did a postdoctoral fellowship in Houston at the Houston Advanced Research Center. And then I was pretty clear that I wanted to come back to India after my studies. I had sort of known that all the years, since the early days of my studies in the US. And so I actively looked for places in India where I could work. For the area in which I work, which is particle physics and cosmology or particle cosmology, PRL was the best place in India at that time. And therefore, I was very fortunate that I was offered a faculty position there, and I moved back to India in 1997, and I was there for 2 decades till January 2018.
So there you were an associate professor, let's say the job.
No, so there are multiple levels. You joined in that structure, and I was a professor when I left.
So from being a professor to a dean here at AU, also you were dean of multiple institutes one by one. So how did this transition from let's say research or being a professor to this key position happen?
Okay, so I'm currently the dean of the School of Arts and Sciences at Ahmedabad University. Prior to that, I was dean of the undergraduate college. So when I first joined Ahmedabad University for the first 4 years, I was dean of the undergraduate college. For a while, I was also dean of students. And then in 2022, after 4 years, I shifted offices and took over as dean of the School of Arts and Sciences. So a research institute like PRL is a very exciting place to have a large number of very active researchers who are very passionate about their subject. And at PRL, we had primarily people in physics and geosciences. But because of my undergraduate experience in the United States, which was at a university, and a university in the US or even in India is made up of multiple disciplines. And it's always very exciting to meet people from disciplines other than one's own. So I was always attracted to the idea of being at a university. But the American university system is also different in certain ways. One is that the undergraduate education requires you to take courses outside of your discipline. So out of the very many courses I took in college, almost half of them were not in mathematics and physics. So I took courses in history, in economics, in modern dance, in theater, and literature, and I enjoyed all of those courses. More importantly, I was challenged in all of those courses as well. It's not like that only my physics and maths courses were challenging and the others were easy, because the students in those courses were getting a degree in literature or history or economics, and the faculty there were also scholars in their own right. And so the courses could be quite challenging and deep. And I enjoyed that. And I always hoped that there would be in India universities like that. Say in the Indian context, if you go to some of the excellent universities for science, like IISERs and IITs, for a very long time they have also included humanities as part of humanities and social sciences as part of the curriculum. But in such institutions, the students are all from technology or science. So when you take a course in psychology or economics, your classmates are all from that particular discipline. Also because they don't offer at least undergraduate degrees from in the humanities and social sciences, you have only a limited number of courses that you can take. While my undergraduate experiences, I could choose from a very wide variety of courses because there were degrees, there were programs in all of these disciplines. And the students in my class were students majoring in it, or not just people from physics or engineering. And that diversity made the classroom discussions that much more interesting. So I always felt that we should have something like that in India as well. Ahmedabad University is actually committed to interdisciplinary and multidisciplinary education. And so when the opportunity came to be associated with the university, it was very attractive and very exciting for me. And so I decided to.
So I was just going through some of your recent work. I'm an MS physics student right now. Is it? So I did not think I was of enough aptitude to understand. Because I was really interested in one of these topics, gravitational baryogenesis. Could you talk something about it? Consider me a lead.
Okay. So let me just talk about baryogenesis in general, because that's an area in which I worked for many years. Baryogenesis is also referred to as understanding the matter-antimatter asymmetry of the universe. We believe that at very early times, the universe would have had equal amounts of matter and antimatter in the universe. But if you look around us today and make measurements, observations, you find that as far as we can see, the universe is made up only of matter. So our planet is made up of matter. You and I are made up of matter. If you were made of antimatter and I was made of matter, or when you shook hands, there would be an annihilation and a lot of energy in the form of electromagnetic radiation or some other form would be released. The moon and other planets are also made up of matter because they've sent probes there. And when they've landed, for example, on the moon, nothing happened. And there are many other observations that indicate that as far as we can see, the universe is made up only of matter. So this then begs the question that where did the antimatter go? So if you started off with equal amounts of matter and antimatter, why is the universe made up only of matter today? Our understanding is that while we started off at very early times with, let's say, equal amounts of matter and antimatter, at some point there was some kind of a disequilibrium and there was a little more matter than antimatter. This antimatter annihilated with the matter, and all the stars and planets, etc. that we see, and you and me, that we see today are made up of whatever was left over from the annihilation of antimatter in the very early.
So where did so much of energy go, sir?
That is just diffuse, goes into other particles, goes into electromagnetic radiation, etc. That is there in the universe even today.
And what caused this?
That is an excellent question. No one really knows. What caused this disequilibrium that changed the amount of matter and antimatter in the very early universe? And when I'm talking of very early universe, it's much earlier than 1 second after the Big Bang. So that is the arena in which one works. There are many models that could have caused this disequilibrium, and I have worked on several of them involving. They come with different labels: gravitational baryogenesis, electronic baryogenesis, black hole baryogenesis, granutride theory baryogenesis. But they're all mechanisms of creating this asymmetry, leptogenesis, etc. And after that, we understand fairly well why these things would annihilate us. So that's something that I worked on, different models, different scenarios for many years.
Baryogenesis is basically this process that...
the matter that we see around us today is made up of maybe atoms or nuclei and electrons. So if you take an atom, most of the mass of the atom is sitting in the nucleus, which is made up of protons and electrons, which are also known as baryons. So the matter-antimatter asymmetry is also referred to as, or generating the matter-antimatter asymmetry is also referred to as barriogenesis, because you're creating a world full of barriers.
Understood. Okay, I visited you first time just yesterday, and talked about you at many places, like one of the Prof this year, and wherever. Also, people here consider you a god.
No, I was heard there now.
Like, they respect you immensely. Of course, everyone respects their lean, but there is some kind of softness for you in their hearts that is
But
I've not seen it anywhere else. So, where does this spark come from? Where is it? What is it?
no, okay. So I think I don't know whom you have met and what I've told you. I'd rather just talk of two things that I think are essential in an academic institution. And I've been part of academic and research institutions for a long time, and also have friends in many of these institutions. I think the two things. One is with regards to how one deals with students, engages with students. I think academic institutions should be student-centric, and Ahmedabad University tries to be that way, and all of us who are associated with it in our own way try to push it. Which means that we will keep students' well-being in mind, and we will genuinely listen to students' concerns. It doesn't mean that we will always agree with their concern or their grievance, but we'll at least give them a hearing and try to address it in what we think is the best way and the fairest way for all members of the university. So I'll reiterate, it doesn't mean that we will necessarily do what a particular student may have complained about or requested, but we will at least listen to them and try to address the issue in what we think is the correct way of addressing. Also in Ahmedabad University, we have put in a system that first point of the grievance. There are multiple levels at which they can approach people in the university. It has been built into the policies of the university. So a student, if they feel that their concern has not been addressed at one level, can take it to the next one. That's one thing. The other is in how one engages with faculty. I would say that in many institutions, there is hierarchy, and sometimes younger faculty are ignored. We have tried, and all of us, I think, at the university are working towards it, to create as little hierarchy as possible at Ahmedabad University. For example, at this university, irrespective of your rank as professor, everyone will be addressed as professor, which is not true in some institutions. Only someone who's at the full rank of professor will be called professor, others will be called doctor, because everyone has a PhD. We involve faculty in faculty hiring, etc. Of course, some decisions will be taken by the deans, will be taken by the executive provost, the vice chancellor, or members of the leadership, and faculty may not like that decision, may disagree with it. But to the extent possible, we do try to, well, not to the extent possible, we do listen and take into account what people are saying. But we may not always, as I said with students, we may not always take a decision that people would prefer victim. And
What is right?
we do what we think is right, taking into account what others have, the faculty have shared in terms of their concerns or suggestions.
In quote, like, considering every perspective.
Yes, and we hope we're right most of the time. I'm sure we also make our errors, and we will learn through that process of creating a better institution for all.
I've got it set with at PRL. What do you think is your favorite contribution?
For a faculty member and a scientist, it's difficult to think in terms of favorite contribution.
Okay.
I enjoyed the research that I did there. There were some papers, the articles that we wrote, which were a lot of fun. Sometimes they may not be cited as much, which means they may not have as much impact, but they're a lot of fun. And some other articles which, were seemingly routine, not as challenging, sometimes get a lot more citations. So if I look at the work that I've done, there are, and it's hard to pinpoint, there have been some of them that I've really enjoyed working on. And there were just the challenge of solving that problem was, very fulfilling. The other is, I used to teach, there's very little teaching at an institution like PR because we only have PhD students. But I would typically teach one course a year, and or something like one course a year. And I really enjoyed engaging with the PhD students at PR. They were a bright set of students. They were lively, and it was fun to interact with them and fun to teach their careers. And that's now many of them are also colleagues.
So you were a part of this advanced PhD program at Xavier's. Yeah, how was your experience there?
So that is something that I feel very happy that we started this in 2003. It's now more than 20 years. The idea was that in physics, in colleges, in the standard colleges in India, what you learn is the theory behind various physical phenomena, and the emphasis on problem solving is not there. Secondly, in colleges in India, you have very good teachers, but very few of them are active in research. We wanted to give college students an opportunity to first of all learn about problem solving in physics, because that's essential, A, to help oneself understand whether one has mastered the subject or not, and 2, because it's required if you want to go to a good institution for your next degree, because there will be an entrance test and it will all involve problems which you need to solve. And we want to also give these students a chance to come into contact with people doing research while they're in college. This is, for example, an opportunity I had when I was in the US, because at my university we had very active researchers in physics, and our exams were always just problems. But this is also true in good institutions in India like IITs and ICERs and a few good universities, where the teaching, the pedagogy is a certain way, and the faculty are also active researchers. So what we did with the Advanced BSc Physics program was create a program that caters to college students. Initially, it was just for students of Ahmedabad and Gandhinagar. On Sunday mornings, we used to have students, first year students, second year students, and third year BSc Physics students come to the Vikram Sarabhai Community Science Center. And faculty from PRL, Physical Research Laboratory, IPR, Institute for Plasma Research, and Space Application Center, S01E04, would come and teach these. Once again, the emphasis was on problem solving. So we were teaching the same topics that they were studying in college, but we would teach them how to solve problems and challenge them. And there were classes in physics and maths. And now they were being taught by people who were very active researchers. So they could mentor them as to, how they could go on for higher studies and good tests. After a few years of this, they were approached by students and teachers of colleges outside of Ahmedabad in Gandhinagar, who said that our students can't come every Sunday to Ahmedabad. Can you do something different? And that's when we moved to a summer school now. So now, so after about 5-6 years, they started having 3-week summer school for students who have finished the second year of BSc in Physics. And we get students from all over Gujarat, from all districts. We seek out students from all over Gujarat. And they spend 3 weeks in the summer school. Once again, the faculty are from PRL, IPR, and other such research institutions. And the emphasis on problem solving. And it has, I believe, been very successful in that many of our students went on for higher studies in good institutions like IITs and good universities. Many of them went on for PhDs in good places in India and abroad. And they have several students now who have already finished their PhDs from universities in the US and in India, and our professors now in institutions.
Must be very proud.
Yes, that's a program that I'm really happy that we started, and that's been continuing for a long time. The various institutions have helped us in this. Vikram Ahmedabad Community Science Center is a partner in it. The Gujarat Science Academy has supported us with financial support. Physical Research Laboratory, Institute for Plasma Research have also supported us financially, along with some other organizations over the years.
Is now when we talk about universe, dark matter, the early universe raised lots of mysteries and questions with to us. Like one of those would what caused that disbalance.
Yeah.
There are many such questions. That's what I believe.
Yeah.
So what is the latest question that the world is working on? Let's say at global level.
So I would say there are three big mysteries in cosmology that we're still trying to figure out. One is, we know that in galaxies, about 90% of the matter that is there is made up of something called dark matter, which is that it is matter that does not give out light and doesn't reflect light. So it just doesn't interact with light, and so we are unable to see. You can see an object if it gives out light, like the sun, or reflects light, like the moon, or there's a bulb over here, it's giving out light, I can see, or I can see you because the light from that bulb falls on you and then enters my eyes. But if you were made up of material that neither gave out light, nor did it reflect light or interact with light, then I would not be able to see. So there's a huge amount of matter. 90% of galaxies is made of dark matter, and we don't know what constitutes the dark matter. So supposing it is made up of particles, we don't know what that particle is. At one point we thought it might be neutrinos, then the axions, all kinds of particles out there that have been hypothesized as the dark matter. And we've been searching for it for the past 80, 90 years, because we knew about dark matter from the 1930s. And about the existence of dark matter, about its gravitational effects. But the properties of this dark matter in terms of what is, or the nature of the particle that makes up the dark matter, no one really knows. Many people would know about the Large Hadron Collider, which is this huge accelerator at CERN in Geneva, where you accelerate particles to very high speeds, protons directly, and you make them go in a circle, very high speeds, close to the speed of light, and you have two beams of particles, one going like this, the other going in the other way, this way and this way, but and then they collide. And when they collide, of course the proton breaks up, you can see what's inside. But because E is equal to mc squared, the kinetic energy of the colliding protons can go into creating mass of particles that are much heavier than the proton inside. So the hope was that in the Large Hadron Collider, which cost only $8 billion, that we would be able to discover the Higgs particle, which was the Higgs boson, which was one particle that we've been searching for a long time. And the other is get a hint of what is dark matter. Either the dark matter particle is produced, or sister particles of the dark matter particle will be produced. So far, nothing on the dark matter front. There are other experiments not using colliders, because dark matter is everywhere. It could come and hit your experiment and you could detect it. But the problem is that it interacts so feebly, if at all, with the material in your detector. It's a very difficult experiment to perform. You need very large detectors, so it increases the chance of something hitting your detector. So far, nothing. So that is one burning question in cosmology. What makes up the dark matter of the universe? Another question is, what is driving the acceleration of the universe? So when I say acceleration of the universe, it means something is growing and speeding up as it's there. So I'll have to say something about what does it mean to say the universe is growing or expanding. A long time ago, based on various observations, we realized that if you look at distant galaxies, they're all moving away from each other. And when you try to explain that, you realize that that is not because these distant galaxies had some intrinsic motion, that something got a kick from something that is moving away, because then you would expect half of them would be moving towards each other, half would be moving away from each other. It'd be random motion. But if basically all of them seem to be moving away, then something else is happening. And our understanding is that the space between them is increasing. Now, it's a little odd to say how the space expands, because one often thinks of space as just the arena in which physical phenomena happen and is non-dynamic. But with Einstein's theory of general relativity that got developed in the early part of the 20th century, the space itself has certain properties. I think it is dynamic, and so one has an explanation of why distant galaxies are moving away from each other. It's because the space in between them is increasing. Now, for the longest time, our understanding was that yes, the universe is, and that is the statement that the universe is expanding. That is, if you take two distant objects, they're moving away from each other. I keep saying distant objects because you might then ask, what about the solar system? Or what about you? Exactly. So, things that are part of a bound gravitational system, okay, this doesn't apply. The local gravity is more important than the large-scale gravity. But if things are very far apart, they're not part of the same gravitationally bound system. And so they're sort of free of each other. And then you can think the only interaction between them is the large-scale gravitational interaction between them. And from Einstein's theory of general relativity, it explains that the space between them is increasing, and therefore they're moving backward. Okay. Now, for the largest time, we thought that most of the universe was made up of, we knew most of the galaxy was made up of dark matter, so we concluded that most of the universe was also made up of dark matter. And the property of dark matter is such that while the space will expand, over time, the rate of expansion will slow down. So that's called a decelerating universe. Because if something is moving but is slowing down, it's a deceleration. Then somewhere around 1998, by observations of the light coming from supernovae, it was realized that actually the universe is speeding. Like the distance between objects is increasing at an increasing rate. And so that's referred to as the accelerating universe. The explanation for that, so the underlying theory that explains how space evolves in time is Einstein's theory of general relativity. As per that theory, if space has to be expanding and accelerating, there has to be something that is causing it. And we refer to whatever is causing this acceleration as dark energy. Is different from dark matter. Dark matter is made up of some particles, or maybe made up of some other bound object or some other compact objects, but it would make the universe decelerate. There is something else out there in the universe which we refer to as dark energy. No one knows what it is. And let me just say a little more. There are two possible ways of thinking about this. One is that in Einstein's equation, you have to put in a modification to that equation, which is called the cosmological constant. And when you put that in a universe with dark matter and baryonic matter, that's protons, neutrons, etc., the universe will be accelerating at some point. Cosmological constant was actually put in there by Einstein himself at an earlier time. And he removed it because he felt that it was unnecessary. But maybe it is necessary. The other possible explanation is that just as like there are protons, neutrons in the universe, which are baryons, electrons, photons, etc., dark matter, you have in the universe a field that pervades through the universe. Now, we are familiar with fields like magnetic field, electric field. So magnetic field, you have magnetic fields in galaxies, etc. So you could have, like a magnetic field, you could have some other field that is all pervades the universe. So all there, all through the universe. And it has the property that it causes the universe to accelerate. So we refer to this field as the quintessence. There are modules, ideas, theories of what this quintessence field will be. or could be right. But as of today, we do not know whether it is a cosmological constant or a quintessence field. And if it is a quintessence field, which one it is, because there are several modules that could work. So that's a burning question. What is dark energy? The third one is related to the Big Bang. So I said that the universe is expanding. So if you take any finite region of space, all the matter that is in there, if you go back in time, the density of this matter will keep increasing like this. If you go back, way back in time, we know that the universe is about 13.8 billion years old. So if you go back 13.8 billion years, what will happen is that this entire matter, which is in this space today, would be contracted to an extremely small region. And we know from our understanding of what was happening at early times, it would be an extremely dense, extremely hot energy. Yeah, so the energy of particles will be very high. So high that atoms and molecules will break down, even protons and neutrons will break down. You will have quarks, electrons, dark matter particles. We call this the primordial soup of very high energy particles. And we also know that at very instant, the universe will also be expanding very fast. This initial instant, when the universe is extremely hot, extremely dense, rather than hot, I'd say extremely energetic. The particles are very energetic, but it's very dense, and things are moving out really fast, is referred to as the Big Bang. Now, when you get to such high early times, such high energies, the energy of particles is so high that you actually need a quantum theory of gravity. Because Einstein's theory of general relativity, which is a theory of gravity, is a classical theory of gravity. There's no quantum mechanics, right? The particles in it may be doing this, and we apply quantum theories too. But the gravitational theory, the theory of gravity, which Einstein gave, which is called general relativity, there's no quantum mechanics. But at those high energies, those early times, you need a quantum theory of gravity to explain how particles are behaving, to explain how space-time is behaving. And we don't have a quantum theory yet. So when people ask the question, how did the Big Bang happen? What exactly happened in the Big Bang? We can't answer that question because we don't have a quantum theory of gravity. People may have heard of ideas or theories called like string theory or loop quantum gravity. These are all quantum theories or theories of gravity. But as of now, we still don't know. We don't have a fully consistent theory of quantum gravity, and so that's another question that we need to answer. An example
About this dark matter and dark energy, as I remember, dark matter is what is reducing the acceleration.
it's causing the deceleration. Yes.
Dark energy is acidity.
Yes.
So is there any relation about dark matter and dark energy? If we just a naming question.
Not really. So there are some few models that try to link them, but in general, dark matter is the only common thing is dark there. If it refers to the fact that we can't see it, we don't know what it's about.
How did we detect intent?
We are detecting the gravitational effects of it.
Based on energy?
No, by observations. So dark matter, we discovered, first it was discovered in clusters of galaxies, that is how the galaxies within a group or a cluster were moving, indicated that there was more matter there than what we were observing. But the other way in which we saw the dark matter was by looking at how stars move in a galaxy. So if you take a galaxy, let's take, you can have a lot of matter at the center. Let's take a spiral galaxy. A lot of matter at the center, which we call the bulk of the galaxy. And then you have stars and going around it. They're also part of the galaxy, but they're outside of the bulk. Yeah. So if you look at Milky Way, and it has spiral arms like this, and look at stars and gas that is in those spiral. If you look at the stars going around the center of the galaxy, you can just apply, anything going in a circle must have a centripetal force acting towards the center of the center. From Newtonian mechanics, yes. So you can do a calculation of that the centripetal force mv squared upon r is equal to the gravitational force acting towards the center. The gravitational force is Newton's gravitational constant g times the mass that is inside the circle, little m, which is the mass of that star, divided by r squared, the distance from the center. Now, for the total mass of the galaxy, if you look at this galaxy, most of it is sitting here, and there's just a little bit of matter that's around. So you can just take the bulk galaxy, in fact, the bulge of the galaxy. So I didn't mean to say bulk, but the bulge. Okay, the bulge of the galaxy. And you can look at stars at different distances from the center. Okay, from different distances from the bulge. Then, if you just apply Newton's laws, what you will realize is that the velocity of these stars should be decreasing with distance. But in galaxy after galaxy, we find that the velocity at different distances is remaining the same, almost constant. Which indicates, if you go back to equating the centripetal force with the gravitational force, I think that the mass in the galaxy is not what we are observing, but there is some additional mass there. See, how do we estimate the mass in a galaxy? You see how much light is coming from a galaxy, and there's the mass to light ratio, so given so much light, you know that so much mass is there. So that's how we were calculating the mass. But
there is some error.
So it's hugely off. Okay, and we will now realize that there's more matter in the galaxy than what we are inferring from measuring the light. And it is actually 10 times more than the mass that is we're inferring based on the light that is. And so that is the dark. So you asked, how do we know that there's dark matter? How do we detect it? This is how we detect it. And now it's been seen in galaxy after galaxy and the other observations. But this doesn't tell us what makes up the dark matter. That if it is made up of particles, that you don't know what it is. See, like you see the sun and it's bright, you don't know what it is. But sometimes you will see solar wind. Sometimes it's there. There are particles being ejected from the sun, and when you detect them, you can say there's certain kinds of particles that are familiar. So we know what the sun is made of, but we do not know what the dark matter is, which makes up most of the galaxy.
That's how we detected dark matter. How did we detect dark energy?
But dark energy was looking at the light coming from various supernovae at different times in the history of the universe. And what you can detect is the speed at which, at an earlier time, it was moving away.
Then compare it.
Because if it was moving, when it is moving away, it's the frequency of the light coming from the stars, from that supernova, will Doppler shift. That is, the frequency will go down. So that gives you a measure at different times, because you're looking at supernovae at different distances. The further away it is, the light from it is coming from an earlier time. So when you look at supernovae today at different distances, we're actually looking, the light that you're receiving left at a much earlier time.
Yes.
So it gives you an indication of what the universe was like at an earlier time. Right? And you can, because of the redshift, the change in frequency of the light, you can say how fast how fast the universe is expanding. And from that data, we could determine that actually it's been accelerating for the last 5 billion years.
So based on these three big questions, what is India doing?
So India, we have a very vibrant physics research community in the country. Much of the research is happening in research institutes like PIFR, PRM, Indian Institute of Science, etc. In institutions like ISERs, Indian Institute of Science, Education and Research, IITs, and at some good universities like Jamia Millia, Ahmedabad University, etc. So in all of these institutions, you have people who are working on different aspects of some of these problems, particularly in the context of dark matter and particle physics. You have a large number of physicists who are working on the theories of what could be the dark matter particle. We also have an experimental particle physics community in India, and our scientists from institutes, universities, at Delhi University, etc., Punjab University, are part of research collaborations like at CERN, and they help in building the detectors, in analyzing the data, and so they have been working very actively. Yes, yeah. So when it comes to quantum gravity, we have very strong groups in India working on theories related to quantum gravity, like string theory. And also in dark energy, there are many cosmologists who have been proposing ideas with respect to
for this communities for Indian scientists, and let's say consider some young students, like pursuing, let's say, MSc or interested in this field. What do you think are the greatest challenges for them that you yourself also felt, and or you feel it right now for them? That is what a hindrance for them to do what they are supposed to do.
I think students, let's say at the BSc level or at the MSc level, should think about their next step for higher studies, should think big, should think about going to the best place that they can go to for their studies, which will not necessarily be in their own city or their own state, and may not even be in our country. So you should aim to go to the best place possible to study. Now, to get to the best places or very good place, it's very competitive to get into this. So you need to not just study what is taught to you in your MSc or what is taught to you in your BSc, but you must be willing to read beyond what is there in your textbook. So in college or in MSc, you have a standard textbook. Let's say you're studying quantum mechanics. Of course, study from that because that's the text for your course. But read other reference books so it will expand your understanding of the subject. Second is, to get into any of these institutions, typically the entrance exam involves problems that you have to solve. Our colleges, our universities at the MSc level usually don't prepare you for that. So you need to do some studying on the side. And what I tell students is that we find old question papers, these are all available, and work on them, try to solve them. Another two tidbits. One is, it's actually very frustrating to try and solve this question. They are hard. So always work in a group. So you're 2 or 3 students working together. Because if I can't solve it, I feel really bad. But if you also can't solve it and she also can't solve it, then I feel, okay, I'm not so bad. I'm not the only one who doesn't understand. 2, I couldn't solve it, but you could solve it. Then you can explain it. Or I understand something and I explain. In fact, in the process of explaining to someone else, you understand it even better. The other thing is that when you're trying to solve these problems, always get problem books that also have solutions. You should challenge yourself. Don't read the solution immediately. But if after you have tried looking at it for 1 day, 2 days, then it's time to look at the solutions. Learn from it. Maybe after you read the solution, put it aside and solve it then by yourself. So you make sure you've understood it. And that is then a stepping stone for you to solve other problems.
It seems like you also had a group of 2 or 3 people back in your...
Yes, we used to. It was fun.
Good enough to go. We share a memory about those days. Your friends group.
So, now that's so long ago, I don't remember.
Thank you.
But I do, when one of us would get the solution, then would excitedly, when you met the person the next day, you would say, hey, look, this is how it works. And you flex it a little bit. No, you're just excited about sharing with someone, and there would be through, or sometimes they'd find an error in your solution, and then you work together to solve today's system.
So, apart from this physics and let's say your professional side, do you have any hobbies, or how do you remind?
I have an interest in history, and I have a great interest in literature and reading. So I usually end up reading every night something or the other. Besides that, I have some interest in social issues and societal issues, and I try to stay engaged with those issues. So
and let's say for our age, we are already 20s, we
Yeah.
have heard this advice that we don't find work-life balance like enough. Just go all in, put your work, and let the work-life balance meet you later in your 40s or something. For your generation, how was it different in your early 20s, and how is it different for our generation?
Okay. I mean, the most sort of obvious difference is that the internet and social media. I sent my first email. I first got an email ID when I joined for the PhD program. And I was really excited to have an email until I realized I didn't know very many people to whom I could send email, because it was still not so common globally. I was in the US at that time. What I would say, because we didn't have so much access to the internet, the World Wide Web is just coming out. In the 20s, definitely. When I was in college, none of that was there. We read a lot. So in school, we read a lot. Everyone read storybooks, and those were more academically inclined, maybe read more encyclopedias or read books in the subject we were interested in. That would continue in college. So I think that made a huge difference in the way we spent our time. If I think today many people would just leave their phones and mobiles aside and focused on certain other things, they would probably find a lot more time. We also had more time for friends, like the actors and friends where we met and chatted, not where we messaged each other.
Actual friends, not the digital friends.
Well, digital friends are also friends, but we actually met face to face and interacted with each other. And I enjoyed that.
About the work-life balance,
So there will be periods in anyone's life where some things have to get done, where there will be a little more intensity of the work. For example, before exams, you have to study and cover the material before some competitive exam, and you have to work very hard. I remember after 12th, my 12th standard board exams got over. I went and watched a movie with my friends, and from the next day I was studying for competitive exams, because the exam was in a month and I had to make sure that I did well. So there will be periods like that. But you can't go through life in this kind of intense mode, because you will burn out. So you must learn to strike a balance between the work and having some time. So one is to have some other passions besides your work, besides your subject of study. So then you enjoy doing those things. If you have no other hobbies, if you have nothing else that interests you, then you're going to find it difficult to spend time on that. So I think all human beings are interesting people, are interesting, and they should be able to find, and the world is an interesting place. You should be able to find at least one more thing besides your studies that interests you. In theater, it could be going for walks, it could be whatever it is, but people should cultivate certain other interests. It just makes them more interesting and makes it possible for them to enjoy life a lot.
Shifting toward the new philosophical field, science usually answers, or let's say ask questions about how and what.
Yeah.
How do you view, and what is your take upon questions with why?
That's a really interesting question. I'm glad you posed it, because actually most people don't realize that science cannot answer why. And I still remember I was a PhD student, and I was at an institute in Europe at that time for a summer school, and a famous physicist came to give a talk. His name was David Gross. He then got the Nobel Prize many years later in physics. And he said, science cannot answer why. And I, as a student, was like, what? I thought that was what my research was. Why is dark matter behaving like this? Or why is matter going? Why is there a matter-antimatter asymmetry in the universe? And the way he explained it, and which is what I'll share, is you could ask, why do two electrons repel each other? And the answer is because of Coulomb's law. Okay, the Coulombic force. Then the next question is, why is Coulomb's law? field. So then you can take a little more, study it, and realize that it comes out of quantum electrodynamics. Okay? And Coulomb's law is a classical law. Yeah, it's a classical. Well, then why is quantum electrodynamics right? Well, because you get it out of what you call the standard model of particle physics, the quantum field theory, which seems to work fairly well, and it implies quantum electrodynamics, like certain energies. Why is the standard model of particle physics right? So you say, okay, maybe it comes from a grand unified theory, which we don't know which is the correct one, or if a grand unified theory thinks is. Well, why is the grand unified, let's say there was a correct, why is that correct? Oh, it comes out of quantum theory of gravity. Why is that theory correct? So you can keep asking the question, why? And at some point, the physicist would have to say, because that's the way the world is, or that's the way nature is. We don't have an answer why it is.
At the end, we would reach at a being to not know.
Or we would say, that's the way it is. Now it comes to a question, then how does one approach the why? You could either be an existentialist and say, well, that the world is the way it is, and that's it, there's no answer to this question. Or you could be religious or spiritually minded and say, it is this way because God made it that way. Which is the correct answer? I don't know if anyone really knows, but it's a personal view that one takes, that this is the way it is.
Means, any of your recent projects that you are currently working on, I did try my best to go through your articles from ResearchGate, LinkedIn. I went through everything, but even your, the subject on which you're working was out of my this aptitude understanding. So what are you currently working on, and how is it going?
So but because of administrative responsibilities, my focus on research is a lot less right now. But largely, I continue to work on questions related to the mathematical asymmetry of the universe, and trying out different ideas and models. Some work, some don't work. When they don't work, you go back to the drawing board and try to tweak it in a certain way. So we were looking at some models of baryogenesis, understanding the matter-antimatter interaction in theories of gravity, which are extensions of general relativity. So Einstein gave us the theory of general relativity. There's something called the Einstein's equation that let's say, can we add some terms to those equations, which is an extension of the theory of general relativity, and see, does that give us new scenarios in which you can obtain the matter-antimatter asymmetry?
Which means, recent advancements, it's like POB on cosmology and particle physics that exciting those,
So I think the detection of gravitational waves, which has happened some time ago, is particularly exciting. It was predicted by Einstein that you will have gravitational waves. So is just as if you have an electron that goes up and down, it will produce electromagnetic radiation. If you have particles that influence each other gravitationally, like things going like this, then it will produce gravitation. But Einstein thought it would be very hard to detect these things. They were very weak, etc. And for the longest time, no one thought it was possible. There were experiments going on for decades and decades to detect the gravitational waves. And finally, we've seen that. And these are signals coming from the collision of black holes or neutron stars. It's really exciting that gravitational waves have been detected. The existence of gravitational waves could be inferred from the decrease in period of binary pulsars. So that was known, that if you have a binary system, two stars, one of them is a pulsar, which is a neutron star that's behaving in a certain way, and you could see the period at which you were getting a signal from this pulsar, and the period would keep decreasing, which meant that perhaps things are speeding up, or which meant that things are speeding up, and in that process also gravitational waves are being emitted, and you never detected the gravitational waves at that time, but you detected the change in the period, and it matched what Einstein's theory predicted. if gravitational waves are produced. That was exciting. Nobel Prizes were given for that. But the Nobel Prize was given for the detection of gravitational waves. That's why actually the gravitational wave had hit the detector, produced something, produced some signal, and it was therefore it's a direct detection, not an indirect influence. Yes. But it also, so that is exciting. That's only part of the excitement. The other is telling us something about black holes, which we don't fully understand. We understand a lot about it, but we'd like to know more about it, more about them, the different masses of black holes that one should expect to see from theories of structure formation in the universe and what we are actually observing. So these are all exciting things, exciting results that are coming from these experiments, and there's a lot more to come.
What is this gravitational wave and it's about black holes?
I'm not an expert on that, but one thing that we've been able to infer is the mass of these black holes that are colliding and which are producing the gravitational waves. They're coming at with different masses, and I believe there are some questions with regards to the masses of these black holes, and the observation of black holes with certain masses and non-observation at certain of certain masses.
You were correctly at a position of authority being said.
Responsibility, that's not but that's very honest. We have that.
At a position of responsibility. What are certain initiatives at especially AU and at other universities that you took and you're proud of that brought great changes, as we talked about this advanced gazing of certain other initiatives?
So in 2019, Ahmedabad University, by the way, we don't refer to ourselves as AU because there are so many AUs in the country.
I mean, and the
yeah, so no, that's perfectly okay. Yeah, because otherwise with AU it's hard to tell which A university, Andhra University, Allahabad University, Ahmedabad University, etc. So when I joined in 2018, the university was going through a process of introducing a new undergraduate program to be launched in 2009. The new undergraduate program was meant to be interdisciplinary, multidisciplinary, flexible, and research-oriented. I had the advantage of having gone through that as an undergrad already. Okay, I had experienced it. So, as Dean of the Undergraduate College, part of my responsibilities were to design the policies and the structure of the new undergraduate program. And I could draw upon my experiences as an undergrad to create something, or to work with others to create an undergraduate program that had the features that I mentioned. So some of the things that are part of the undergraduate program at Ahmedabad University are a student takes about 30% of their courses from outside of the discipline. So physics students are taking history, they're taking literature, they're taking gender studies. Engineers are taking sociology and psychology and music. Management students are taking biology and data science. So this kind of an undergraduate program, designing it was a lot of fun, and we're very proud of what we have done. Because we believe at the undergraduate level, it is important that students get exposed to multiple disciplines. The flexibility in our system. At Ahmedabad University, you can come in saying, I want to major in physics, but after taking courses in social and political sciences, you realize, hey, I enjoy that more. You can shift. And we've had students do that. They came in physics and they left with a degree in social and political science. Students came in saying psychology and graduated with a degree with a BBA degree in marketing. That kind of all it takes is for a student to meet the faculty involved with this. We have a conversation to make sure that you're making an informed decision and it goes through. We even have an option at this university of coming in as an undeclared program student. You can say, I'm 18 years old. I don't know whether I want to get a degree in psychology or something in marketing, or in physics, out of fees. So whether it's a BA honors or a BS honors or Bachelor of Science and Management honors, I don't know what degree I want to get. So you can come in as an undeclared program. Your degree is not known at that. You take courses at the university. After couple of semesters where you've taken courses in multiple disciplines, in the disciplines of your interest, you realize what actually interests you. You then declare your major at that, your discipline at that point, and your degree gets decided at that.
It's really good.
So that I think is, in designing all the guidelines for that was something that I worked on. And the research orientation comes from the fact that we have a thesis or a capstone project in your final year where you work with faculty who are active researchers. So, and of course, all through your coursework, you're taught by people who are active researchers. My office was also involved with promoting something called the undergraduate research program where students can work on projects with faculty. So those first 4 years at the university where my office was directly involved with defining many aspects of the undergraduate program, including a very interesting interdisciplinary program called the Foundation Program, was very exciting and something I was very happy to be associating with.
That's great. At distance, it's like behind that you're always working about you and just talk to it your assistant to my concept experienced. I found out that your day is just full of. Could you just take me through your day? How does it look?
I really don't want to. No, it is busy. That's just because we're a young university. Okay. So let me say, when I was at PR, a well-established institution set up in 1947 by Vikram Sarabhai. When I joined it in 1997, things were all in place. So we focused on our research. Of course, the institutions keep evolving. We and other faculty would make suggestions and, bring in some changes into the institution. But largely things were set. So we were focused on research, teaching to some extent, and a little bit of institutional responsibility. At a university like Ahmedabad University, we're very young. Universities globally are hundreds of years old. We are only about 15 years old.
I understand.
So, all faculty, and more so the deans, etc., are very actively involved in making institution building change. So, establishing, creating policies, establishing procedures for the university. So yes, that does take time. And when I joined the university, I knew that, that it is going to take up a lot of time. To some extent, it's a labor of love. You're being part of something that's kind of exciting, interesting, and the amount of effort you put in, the ideas you bring to the table will transform and, modify, bring about some change in the university, but still evolving at a very early stage. And so, yes, one is busy, but that's okay. It's time. And there are periods in your life when you are working on a very important project that you do get experience. You can
understatements. And if the insurance that let's take me or any other, say bachelor students who has inspired so much from you, who wants to make up another professor in Raghavan Rangarajan. So, what would be your guidelines and advice to that?
But so, let's just say that there's a student who is passionate about their subject and wants to make a career in it. In the context of science, largely, and let us say that they want to become a researcher. In the context of science, it's either being in academia, it's being in industry. Though in the context of India, there are very few companies that actually do very much cutting-edge R&D. There are some, but few. Or you could be in research organizations like ISRO and DRDO, which do a lot of research in the sciences, in physics in particular, but they're mission-based. So there are certain fixed objectives and you work on this. In academia, you decide on the problem that you want to work on. Once again, if you're working in the industrial research lab, it's based on the priorities of the company. So these are the options in front of you. And in India today, industrial research lab, a few are there. Academia, there are lots of good institutions, like the ones I mentioned earlier, good universities, good research institutes, good IITs, good ISRs, and a few of these institutions like DRDO, CSR labs, ISRO, etc. The path to becoming a scientist is fairly straightforward. get a bachelor's degree, you get a master's degree, you get a PhD. We also have to do postdoctoral work in general, and then you get into one of these positions. The important thing one has to ask oneself is, do I have the interest and do I have an aptitude for it? The interest must come from within. You should not do physics or engineering or medicine or history or anything just because your neighbor's nephew is doing it and they got a great job and that's why I should do it. No, that's not. You have to look at the subject, try to understand, am I excited by it? Talk to people in the field, what do they do? Because in college, you're only introduced to textbooks and you learn from them. But if you talk to people who are practitioners, they'll tell you what it's about. Okay, so talk to them to figure out if you have an interest. Second, which is important, is you have to ask yourself, do you have an aptitude for it? See, I have many students who come to me saying, I really enjoy physics and I love cosmology. I want to learn about the stars, but I don't like mathematics. Now, mathematics is the language of physics. So it will be extremely difficult for you to do well in physics if you don't like mathematics or if it doesn't come easily to you. And so you may need to reconsider whether this is the correct line. So both interest and aptitude are. So that's what I tell young people. Figure it out. And no discipline, no line is more prestigious than the other. The line, it could be filmmaking, it could be writing poetry, it could be doing physics, it could be doing medicine, it could be doing history, CA, engineering. If you enjoy it, then it's the right thing for you. And if you have the aptitude for it, don't worry about what the world tells you that this is more prestigious than them. It is true that some professions will give you more money than no. But if you have an interest in a profession, in a discipline and have the aptitude for it, generally you will be successful in it because you enjoy it and you have the aptitude for it. And you will generally have a reasonable standard of. But that's the first thing I would tell. First, figure out your interest in it. Second, let us say that you have figured it out and it is science or it is physics. At all levels, bachelor's, master's, or PhD, it's going to come any year. Listen, keep reading beyond what is required of you. Right? So read books, textbooks, the reference books, solve problems, talk to people in the subject and the discipline and try to do projects. Like, as I told you, I realized I was not meant for experimenting physics by doing a project in labs, okay, and realizing that I wasn't quite cut out for it. Similarly, a student should, at the BSc level also, can try to get projects. So, I also tell young people that you have to make the science happen for you, which means you can't wait for a project to just come to you. If in your city there is a university, go to that department of physics or whichever subject you're interested in, knock on a few doors, see, first read the profile of the faculty there, see what they're working on. Then, and if you find something interesting, knock on their doors and say, can I do a project? It may just be a reading project, but you will be learning something outside of what's in your textbook. You may even do some calculations, may work in a lab, and you'll get the experience of what it's like to do research. You have to be, you can't stay within the shell. You will need to get out, knock, explore. Maybe the first person will say, sorry, I'm not interested. May even bark at you. But I'm sure some door will open. If you have a research institute or some very active academic center in your city, go there. Go to the best places around. Don't be shy. And then, as I said, try to get to the best academic institution that you can, because it's really important to study at very good places for two reasons. How do you define a good places? Can be prestigious in certain ways. In the context of science, it will be the better places are the ones where people are doing research. So you will be mentored by people who, let's say you go to an IIT for an MSc, you will be mentored by very active researchers. Secondly, your classmates, because it's a good institution, your classmates are also enthusiastic and about the subject because they've studied hard to get in. With many college students tell me that, hey, I'm really interested in physics, but in my class of 60 students, only 5 of us were really interested. Think of the professor who has to teach that class. How do they bring in additional information when most of the class is not interested? Okay, different colleges, maybe more students, but it is a challenge for them. But if you're in a class that everyone is motivated and interested, the teacher is going to teach a bit differently, and you will learn from your classmates because they're also motivated, and they will motivate you to also achieve and do better. So that's why it's important to go to the class.
You said. Any concluding message for our viewers? Any message you would want to be?
Well, when I was in 12th standard and I had decided that I want to do physics, I want to go BSc in physics. Many people were aghast. They said, and this is not that. You're a good student. You should do engineering. And luckily, my parents are both academics, and they gave me the freedom to study what I wanted. And I was fortunate, and I could study. And then a whole world opened up in front of me, and I realized that there were lots of opportunities. Actually, because my father was a professor, I knew that one can always be a professor and have a fairly good life. So I knew that it's not. There's a wrong impression that if you go into science, you will starve or you will not get a good position, etc. There are many good positions open, and you can be financially. It's very financially viable. So don't be deterred by the fact that people around you are asking you to pick some other profession which is financially more lucrative. But I should also warn you about one thing, which is that to get a position in a good academic institution, it is extremely competitive. And just because you have a PhD, it does not guarantee that you will get a faculty position in a good place or a position in a good institution, in ISRO or in a company or something like that. So it is competitive, and you may not get such a faculty position. However, I have never seen someone with a PhD in physics stop. Because there are other skills we pick up along the way, the ability to solve problems, computational skills, etc. And if it turns out that one is not getting a position in an institution of one's choice, one is able to leverage the skills that one has picked up while you were studying to get a position somewhere else. So I would say to young people who are passionate about their subject, about whichever subject it is, go for it. And if things don't work out in the end, there are often other things that you can do that will still make it possible for you to lead a relatively comfortable life.
So as we concluding it, we really thank you. We are really thankful to you for giving us this always and certain time with us. So very much, sir.
Thanks a lot. I enjoyed talking to you too.
Thanks.